I'd like to introduce Dr. Mark Schenk, please.
Cool, thank you very much for coming, everyone. So I am a mechanical engineer, but I'm an aerospace engineer these days. So a lot of examples I'll be showing today are aerospace engineering examples. So my topic today is going to be origami, and it's a topic that is not necessarily associated with engineering per se. And that's what I thought when I did my PhD. I wasn't expecting to get a PhD in origami, but here I am, fully qualified folder. So my topic for today is going to be origami, and the goal is that after this talk, I want you to kind of walk away and think about origami more than just a pastime, but also as a really exciting topic to do research in, and how we can use it for engineering applications. So let's start with the basics. What is origami? And it literally means paper folding, from Japanese ori, to fold, gami, from paper. And it's something that we tend to associate with Japan quite a lot. And it's also something that goes back quite a few centuries. So 18th century, in Japan, there was a kind of book where they folded the classic crane. And this is always the question I get asked, can you fold a crane? The answer is actually no. But I'll show you cool things that I can fold a bit later. So this goes back a couple of hundred years, and it's quite a classic thing we tend to think about. And in Japan, it has quite an important meaning. So folding one crane is fine. If you fold 1,000, on the right, you have eternal good luck. So if you have the patience, just fold 1,000 cranes, and you're all good to go. And this is the classic one that people always associate with origami. This on the right or on the left is also an origami crane. Folded from a single sheet of paper by an origami artist called Robert Lang. And he is one of the premier origami artists of the 21st century. And I hope you can agree this is slightly moved on from the classic crane. It's a slightly more advanced design. And the cool thing is, Robert Lang is not just an origami artist, he is also a scientist. He's probably one of the world-leading origami scientists. He's known for the crane, but also the moose is his famous one. If you think these are quite advanced, this is probably the most advanced bit of origami I've ever seen. This is a single sheet of paper. So I can't fold a crane, I certainly can't fold this. So this is really quite beautiful. Personally, I prefer things like this, which are a bit more stylized, mathematical. And again, this is again by an artist called Jun Mitani, who is a computer science professor by day, origami artist by night. And the cool thing about this is he understands the math behind the origami as well as being able to fold origami himself. And that's kind of the thing I want you to kind of take away from this, is that origami is not just art, there's also quite a lot of math involved, because that's Robert Lang's crane, that's the fold pattern. So if I gave you that on the right, you should be able to fold the thing on the left. Well, very few people can. But there's something underneath this art. Underneath the art, there is this mathematics which makes it really interesting. And Robert Lang is the artist behind this, and he wrote software specifically to be able to design things like this. So he wrote the software required to actually make these pieces of art. And as I was kind of preparing this talk, this kind of idea of math underlying this art and kind of making it extra special reminded me of a documentary about Richard Feynman. So I don't know if ever you've seen this documentary. It's a documentary from the early 80s, The Pleasure of Finding Things Out, talking to Richard Feynman. And he's discussing how science, he's a physicist, so how physics kind of really kind of gets to his worldview. And there's a scene where he's talking about an artist friend of his who holds up a flower and says, "Oh, this is really beautiful. I can see how beautiful this is. But you as a physicist look at this and you break it apart into atoms and bits. You really take away the beauty." And Feynman gets quite upset about this. And he gets really kind of, no. I can see the art, but I can also see what's underneath. I can understand photosynthesis. I can see how this evolved. So insects are attracted to these flowers. So he kind of argues that by understanding the physics, the flower gets more and more beautiful. And again, I guess my premise for this talk is, if you can appreciate the beauty of origami, perhaps if you understand a bit more about what's underneath, you see it's even more beautiful at the end. So we are going to do some math today, I'm afraid, but I'll keep it quite simple. So before we go down the engineering and the math side of things, there's another thing that Fineman kind of made me realize is that we aren't the first to start folding things. So nature was there quite a while before we were. So here's an example of nature doing its best to fold, and they tried to squeeze this kind of leaf inside a bud, and then the engineers looked at this on the right and kind of extracted these kind of fold patterns and said, actually, this is how nature folded this leaf. That pattern will come back a few times in this talk. It's quite a well-known pattern. So this is origami used in nature to fold up things to fit inside a bud. That's a very classic example. Here's another one, an insect. The wing has to fold up really compactly to fit behind the scales of this earwig, and it has to fold up really compactly, unfold, but actually more importantly, once it's unfolded, you don't want it to fold up by itself again. So this is a really smart little trick where it unfolds and it snaps into place, becomes really rigid, and you can fly, and then you can snap it back and it folds up really compactly. So nature has quite a few tricks up its sleeve when it comes to origami to package things, to deploy things, and it can even do things that we still can't do because we cannot fold rock. So this is basically nature folding rock over a few million years. So nature can do a few tricks, and as engineers, we wanted to kind of repeat those tricks and understand how origami works and how we can use it to solve problems. So in this talk, I want you to show you how we can go from the art of origami through mathematics to applications of how engineers apply it to solve problems. And we have to understand a few of the rules of origami. If we understand some of the mathematical rules, we understand how we can apply it and how we can use it. And we'll be going through quite a few random connections. We'll have Mona Lisa turning up, shopping bags, transformers, and satellites will all come in this talk, all linked together using origami. So let's start a little bit about the mathematics, because we have to do a tiny bit of math to understand, to best appreciate origami. And there's kind of two questions that we have to kind of ask ourselves is, what can you fold? Well, dragons, clearly, but what else can you fold? And if you have a fold pattern, what can you actually fold from that particular pattern? So these kind of two questions we'll be covering a little bit in the next 10, 15 minutes. So the first one is, what can you actually fold? Because if I give you a flat piece of paper, and I tell you you can't cut this, you can't tear it, all you can do is bend and fold it, or bend it, there's not much you can do with it. So I can't twist it, it will tear. You can hear it tear up, got some spares. You can't twist it, you can bend it, there's not much you can do with it. So actually it turns out that you can't really do much with a piece of paper, and you all know this problem, because since childhood you've known that if you've got a sphere or a globe, the moment you try to make it flat, it distorts and warps. So the flat piece of paper doesn't also wrap around the sphere. So you're limited with this piece of paper. I can't make a sphere out of this. It won't work. These are my only two equations in the entire presentation, but the very simple underlying trick is that this piece of paper has a very different geometry than the sphere. But it also limits us what you can actually do with origami. So I have to do something other than bend this to get the nice shapes. And the trick is to add folds. And the moment you start adding folds, you still get these nice curved surfaces between the folds, but these sharp lines make it possible to get these wonderful shapes. Again, this is a really famous origami, well, famous in a very small field, origami artist called David Huffman, and he made these wonderful sculptures back in the 60s, actually. And he wrote this paper, a seminal paper called Curvature and Creases. So he understood the math behind mathematics, behind origami, and he was able to describe these mathematically as well as make them. And it took another 30, 40 years before we were able to do these particular designs again. So adding these folds to it makes it possible to get this piece of paper into shapes you can't otherwise get, because just bending it doesn't really get you very far. So folding is something that really, so these sharp lines in the material that make all these shapes possible. And folds seem very artificial. It's like you and I kind of making a really sharp line. It feels very man-made. But actually, it's a very natural thing to do. So if I took this piece of paper, and rather than trying to bend it nicely, I scrunch it up. And physicists have done this. They have taken a piece of paper, scrunched it up, x-rayed it, and tried to see what was inside. So if you think origami is an interesting topic, try scrumping a piece of paper and calling it research. But if I unfold this, if you look closely, there are actually quite sharp lines here. Paper wants to fold into sharp lines because it turns out it's energetically favorable to kind of get very sharp lines rather than very smooth ones. So actually, paper or very thin materials want to fold rather than nicely bend. So actually, this is the way it wants to deform. And this is where the Mona Lisa comes in, because you might see the smile of Mona Lisa, I see the wrinkles in her sleeve. Because if you kind of push up your sleeve, you'll get these very kind of defined fold lines. And I look at that, I go, ooh, mountain fold, valley, mountain fold, valley. That's what I see. So kind of academics going home, we kind of do see the world slightly different than some of you might. I see origami when I go Leonardo da Vinci. So folding is a very natural thing to do to thin materials, and it allows you that freedom to get interesting shapes. So this might not look like much, but if I look closely at it, I can see fold lines, I can see where fold lines meet, which we call a vertex, and I can start seeing a origami pattern. Well, frankly, if I take a piece of paper and I scrunch it up, I won't get my crane. But you can hopefully see a bit of a parallel between the straight lines here and the fold pattern over there. So the questions are, if I've got this origami, I can fold it, I can't stretch it, I can bend it, I can fold it. What shapes can I actually get? That's one question. And the other question is, if I've got a fold pattern like that, can I actually fold it? The first one has been proven, kind of demonstrated, that you can fold pretty much anything. So on the left, you see the Stanford Bunny. For those who do computer science, it's a classic thing you would use in computer graphics. And it's, I don't know why they used it at the time, but they picked the Stanford Bunny. And what Tomohiro Tachi, top right, he wrote software that can basically turn any shape like that into a fold pattern. Go to YouTube and see him fold this. You can see the daylight kind of passing in the background as he's folding this. But he manages, from a single piece of paper, he can fold that. And he's proven that within some, so I'm not a mathematician, so hence the asterisk next to anything, I'm sure there's limitations. But you can pretty much fold anything you want. And you can get a flat sheet out of it, and you can then fold it up. And you can download software called Origamizer from his website, and you can just get these fold patterns and then spend a day or two folding it. So this, even though we can fold this, engineers tend to think this is a bit too complicated to do anything useful with. So actually, even though we can do all these cool things, we tend to simplify it down to slightly simpler patterns. Not cranes, even simpler things that I can actually fold. So this is the pattern that most engineers will know very well. It's called the Mural Ori. And it's a very interesting pattern for two reasons. I'll explain the two reasons later. It's flat foldable and rigid foldable, and I'll explain what that means. But this is a really interesting pattern, and we use it quite a lot. You can spend your entire PhD looking at one, for example. And this is an example of one of them. It folds, well, it starts out large, and then folds up really compact. And as it does it, it expands in all directions. And this will come back in a few minutes' time. And this is a very well-known pattern, and it's named after Professor Miura. So I'm lucky enough to meet the man a few years ago. He's a bit of a legend in the field. And he came up with this pattern in the 70s, and it actually came from not quite folding up your sleeves, but something very similar for the engineers among us, a buckling pattern. He was looking at buckling of a cylinder, and he saw these patterns, and he came up with this fold. And he's done some really cool things with it. So he started off as buckling. He then looked at sandwich panels. He then also developed a map. So here's one of Miura's maps. The idea was that if you've got a map in the car, it's really hard to kind of fold it up. And he thought, actually, if you use my pattern, I can just unfold it in one motion. So he kind of didn't get rich of making maps, but he got known for making maps. And also, one of his patterns actually flew in space. So he used this pattern, so this very pattern, he used it for a deployable solar panel in space. And we'll come back to that a bit later. But on the right, bottom right, you see kind of a drawing of this pattern. So it's very large array. It folds up very compactly, and you can store it for launch and deploy it in orbit. And we'll come back to that a bit later. And on the top right, you actually see a picture of the mission where they tested this particular design coming from the space shuttle. So this is a very well-known pattern in engineering, so pretty much every single engineer who works in Origami knows this pattern. And frankly, even having seen it for many, many years, I still find it's quite pretty. So it's also the background to my talk. So if you go back, it sits behind every single slide. So this is a really cool pattern, and the engineers love this pattern because it's got two very interesting features. So firstly, it's flat foldable, meaning if I start out as a flat sheet, it starts out flat in the first place, so it's a flat sheet of card. If I fully fold it, it's again flat. Well, it's not entirely flat because paper got a thickness, but it means it folds up really compactly. So if you're trying to make something which stores very compactly for launch in orbit, for example, you want a pattern like this, because it's really compact to fold up. There's another feature why engineers love it so much, because they understand it. There's an interesting thing about this. If you were to make this, not from card, but let's say you were to make this from metal panels and hinges, so proper mechanical engineering, steel and hinges. So you replace the folds by hinges, so like a door hinge, the panels by rigid objects, it will still fold. And that's quite unusual, and it's called rigid foldability because we assume rigid panels. Now, why is it so useful for deployable structures? Is because if I were to make an engineering version of this, where again every fold is a hinge and the bits between are rigid panels, in theory, in practice not quite so, ask my PhD student, in theory, if I were to activate one fold, this entire thing would deploy completely. So the idea is that if I just change one fold, all the other folds will simultaneously deploy, which is not the case for the Dragon or the Bunny. There, every single fold has to be done separately. But here, if I change one fold, the entire thing will deploy. So engineers love it for these two reasons, because A, we understand it, B, it's very compact, and we can actually model it and make it. So this is a thing, you'll see this pattern coming back a number of times in this talk. So, oh yeah, forgot about that. So rigid folding is not something you would see, obviously. It doesn't happen, you have to really design a pattern to be rigid foldable. So if you were to get this is a classic example, so you can see what engineers get published in really good journals, writing papers about shopping bags. So if I get a classic shopping bag, I can't actually fold this without bending and twisting the paper. So if I were to fold this, I have to really, you can kind of hear it, but I have to deform the paper to make it into a shopping bag. So this is not rigid foldable, because I have to bend and twist the bit of paper between the folds to actually deploy it. So these engineers came up with a folding bag, shopping bag, which actually folds rigidly. So if you were to if you wanted a steel paper bag, a steel shopping bag, you could get one if you're really keen. Actually, there's a reason why you don't want that, because this is really easy to fold and unfold, and this one stays deployed. So there's actually a reason why we make this pattern the way it is. But these are two interesting features. This kind of comes back to, if I have a pattern, how does it fold? Flat foldability is important, and rigid foldability is important. And that's kind of takes us away from the math. So there's two things I want you to remember from that. It's quite hard to just bend the piece of paper, to do anything interesting with a piece of paper without folding it. Folding is actually quite a natural thing to do, because if you scrunch it or you roll up your sleeve, you get folds. And we can fold pretty much anything we want if you've got the patience to do it. And the reason we want to use things like the Mural Ori is because they are quite easy to use to actually fold and actually do interesting things with. Because that's the second part of this talk, is what can I do with origami? So if I've got this art, I understand some of the math behind it, what can I actually do with this which is interesting and useful for engineering applications? So trying to solve problems using origami. And I've kind of categorized what we can try and solve in three kind of topics. So one is we can make transformers. We can make things that can change shape and fold themselves into a 3D object. We can also make designer materials. We can make things that behave in different ways depending on how we fold them. And the last thing is deployable structures. Kind of like the solar panel that Miura made, we can make some things that's small and then deploy it in orbit. So I'm going to work my way through these three topics and show you examples how we engineers want to use origami for applications. Applications. So start with transformers. Because, like I said, if you're a really good origami artist, you can fold pretty much any pattern. But if you want to do an engineering application, you might not want to fold this by hand. So, for example, here's again the Mural Ori, but this was folded automatically. So this was basically put into an oven, and it kind of automatically folded itself up. So no kind of human touched it, well, making it, but it's self-folded. So it transforms from a flat sheet into a 3D shape. And you can make this at home, because this is essentially layers of cardboard sandwiching pretty much cling film. So when you heat up the cling film, it wants to contract. And as it's trying to shrink, it folds up the pattern around it. So this is again, we can publish things on paper in cling film. It's really quite nice. So you've got, so this self-folds. Now this Mural Ori pattern is not that interesting by itself, but we can do cooler things. These are all Miura-like patterns, so these are variations on this pattern we had before. But if we can fold this automatically, perhaps we can fold these things. So I can start off with a flat sheet, put it in the oven, or heat it up, and it will then fold into these fantastic shapes. And these might not be that useful, but you might have other shapes you might want to automatically fold to. So these things self-assemble from a flat sheet into a 3D structure. And they do that by folding all the folds at the same time. So you basically start with a flat sheet and it automatically comes into 3D. But perhaps that's a bit too restrictive, because if I want a real transformer, I might want to decide I want this fold first, then that fold. So perhaps ultimately we can fold my bunny by controlling each individual fold. So here's a technique which is very similar. So rather than putting it into the oven, what you've got here is the same technique at the fold lines. You've got this kind of plastic which contracts, but now there are little kind of wires running over the fold line. So you run the current through it, it heats up, the fold line will automatically fold. So here you can kind of do single folds, you can fold a crane if you want, but you can do all the folds by order. So you can automatically program this thing to fold in a specific shape. And the crane is perhaps not that interesting, but this is a paper published in Science a couple of years ago now, where they made a self-folding robot. So on the top, you've got a flat sheet of material, some batteries on top. They send in the signal, the batteries run a current through the circuitry, it starts folding up, and then in the last step, it kind of folds up and locks into place, and there's a motor which turns, and this thing just walks off, which is really quite fun to see. So it's completely kind of programmed. So it folds first the legs, stands up, then locks into place and walks off. So it starts off flat, and it does take about 10 minutes. So I didn't show the video because it's not the most riveting bit. But it then walks off. Now, you can scale this down. That was in the centimeter scale. You can see these are 9-volt batteries to give you a bit of an idea for scale. You can scale this down. So this is the idea behind this, a little origami pattern that kind of wraps around some medicine or something you want to have somewhere in your body. You swallow this, and then the idea is that using some magnetic field, this might walk its way through your guts to the right spot, unfold, and release the medicine. So this is folding it down to fingertip scale. We can go down smaller. So this is an origami crane, and if you look at the kind of the scale bar, that's 100 microns, so that is 0.1 of a millimeter. So this entire crane in red is smaller than the thickness of a penny coin. So the thickness of a penny coin, that's the size of that crane. And they can fold even smaller. They're folding graphene sheets at the moment, which are single layer, single atom sheets, and you can fold that using origami. So this is the idea that we can make things automatically fold and have robots which can walk through our bodies. And ultimately, we do want real transformers, but we are a bit limited, because here, I've picked a fold pattern, I've got the pattern, and it will fold into the one shape. But there were some researchers who thought differently, and they made a universal pattern. So top left, well, on the left you see a small sheet that's about this big, and what they did there is they've got a single crease pattern, and it can fold in two different shapes, a boat and a plane. Just by kind of controlling the currents to the right fold, they can control how it folds. Now, you can imagine this becomes a bit harder to do for my bunny, for that kind of 3D bunny, because you need lots and lots of wires to control and fold it. But this is the future. People want to be able to make morphing structures, transformers, which start from a flat sheet, and you can achieve different 3D shapes. So that's kind of one aspect. This is the transformers. Flat sheets become interesting 3D objects, which can then change shape afterwards. Then we also are able to use origami for completely different reasons. We might want to make new types of materials around using origami. And this essentially, these are pictures from my PhD thesis. I had to put them in somewhere. So my PhD was entirely about this pattern and understanding it. And the idea is that you have this origami pattern, and by not only controlling the material you're using, but also the pattern, you can control how stiff this is or how this behaves. So by changing the pattern, I can make it stiffer or less stiff in different directions. I can twist it. I can deform it. So the idea is that we can use origami as a way of creating materials which have properties by design. By changing my pattern, I can design different behavior into it. And you might wonder why we would want this. Well, one of the reasons I was looking into this at the time was morphing aircraft was one of the motivations. I might have a wing that can change shape and twist. Well, you might wonder, yeah, so it's not a good idea to have origami as a wing. I agree, but I didn't know that when I started. But the idea was that you can then change shape. Well, not only can you have single sheets, we can also combine these. So we have these materials, we can tune the properties by changing the folds, but we can also stack them up. So rather than having single layers, I can stack them up. So this is basically kind of a set of these patterns all combined. I can create 3D materials which have different properties in different directions. So this will expand in all directions. So if I pull this, it will expand in all directions. And also I can design material properties into it. So it's very, very soft that way, but this way it's really, really stiff. I could stand on this and it wouldn't fold up. But that way, it would definitely fold up. So I can make these materials which have really interesting properties just by tuning the fold patterns, and we can make different types of behavior out of it. Yeah. And for example, this is something I didn't see coming because I was looking at origami, as I said, for morphing wings, having things that can bend and twist and change shape. After I did finish my PhD, some people continued this work and they used this pattern as the idea that it's very soft in one direction, stiff in other directions. They used this pattern as a shielding for American football helmets. So what started out as a morphing aircraft became padding for a helmet, which I didn't really see coming. But it's a way of using origami because you can tune its properties, how it's stiff in one direction, soft in another, and you can tune the properties. And lastly, as an example of design and materials, we can design how stiff it is, how hard it is, how strong in different directions. We can also do some other cool things with it. This is some very recent work where they printed circuitry on top of my origami sheet. And what they did, they could basically remove different frequencies of radio signal. So by the spacing of the little kind of bits of metal, they could make it invisible to certain radio frequencies. But by changing the pattern, they could change that frequency. So they could basically have a sheet where they deployed it and expand and contract, and they can filter out different frequencies. So basically, you've got an invisibility cloak with so transformers and invisibility cloaks we can do with origami. So that's two aspects: transformers, designer materials, and the last thing I want to talk about is deployable structures. The idea that I can fold these things up and expand them where I want them. So here's an example of an origami stent. This is something that you would kind of insert into an artery. It would deploy, expand, and keep the artery open. So this was an origami pattern made from a shape memory alloy. So it was really compact. You inserted it, you heated it up slightly, and it would self-expand to open up the artery. I don't think they got it down to the right size, but they were trying to explore getting it that small. So this is a medical application where you might want a deployable structure. Other cases where you might want a deployable structure: civil engineering. I might want a bridge. So the green and yellow one in the middle is a bridge-like structure which folds up really compactly and then deploys. Now here the challenge is, kind of like my shopping bag, I might want something which deploys very easily, but it still has to be stiff and strong when deployed. So you want something which is really flexible, deploys, but once it's there, it has to be strong enough to carry a load. So they did a lot of work on developing these. So the basic building block is one of these tubes where they're going to build these deployable structures where this is truly rigid origami, where if I squeeze one fold, the entire thing will deploy. So they can use these kind of building blocks to design these deployable structures which would deploy and then lock into place. And ultimately what they would like to do, if the video works. Yep. This is still somewhat in the future, but you might have a kind of stadium-like roof that would fold up and then deploy. So this is where they want to go and take these engineering structures, these civil engineering structures, to larger scales. Now, the last application of origami for deployable structures is in space. And this is where the idea that I want to fold something up very small, it has to fit inside a rocket. I launch it into orbit, and once in orbit, I unfold it to a large scale. And this is kind of one of the driving ideas behind using origami for deployable structures, is the space application. So I've got a few examples here. We'll go through them in later slides. But top right is Miura's satellite, where he had this kind of solar panel which deployed. Bottom right is a solar sail. I'll come back to it. And here's a kind of a wrapping pattern where that array there will kind of fold up into a small bundle. But these are kind of really exciting applications of using origami in space. But actually, one of the earliest satellites ever launched by the US had a origami in it. So this is a picture of a satellite. So it's a very, very early one. So 1964. It's called the Echo Balloon, and it's so this is, 135 feet, so 40 meters. So it won't quite fit in this building. It's kind of that size. It's a very thin membrane, and the idea was they would use it, they would launch this, and it was up in orbit for a couple of years, and you could bounce radio signals of it. Now, this was origami because that thing is 40 meters. Rockets weren't that big, so you have to fold it up. And, well, just for scale, that is a person. Can you imagine having that job, sitting there, kind of legs crossed, looking at your thing you've just unfolded? Because that thing fits in that little capsule. So origami, this is one of the first satellites. Origami was used to make that fit in the small box over there. But yeah, I wish I could time travel and be that person and just look at this beautiful thing as it inflates. So this would be inflated in orbit, but then they would release the gas and it would just stay in that shape afterwards. This is one of the earliest ones. Another one would be this one here, which is a deployable solar array. So this would fit, this is about 2 meters diameter, and this will fold up to about a package that big. And the idea is that if you're in orbit, you need power. Power comes from sunlight, so you need a large area to get the power you need to run your satellite. But again, you need to fold up very small before you launch it. So this folds up into a small bundle. So this is where you want large arrays. And same with Miura. His array was a large panel that deployed to get more solar power. Now, you can use the sun not just for power. You can also use the sun for propulsion. So this is launched a couple of years ago, where they deployed a 32 square meter solar sail. So this uses sunlight not as a way of generating power, but actually as propulsion. So the sunlight actually pushes the spacecraft along. So literally the photons hitting the sail will push the spacecraft along. Well, for that to work, you need it to be very large and very light. So this is where Origami comes in. You can package this very thin membrane up in a really small package. So the reason I'm showing this, it's quite a small satellite. So that satellite over there is a CubeSat. It's about yay big. And from that, they managed to unfold this sail. So you can kind of see the silvery stuff is the thin membrane. Just for size, the 32 square meter is about 5.5 meters by 5.5 meters. So this podium is 1, 2, 3 and a bit. Add 2 more steps and then square. That folds into a box that small, which is quite a challenge. And I know this because I worked on a very similar project around the same time. This was 2015 when they launched this. I worked on something very similar around the same time. And this was a sail we made. And we did about half the size. And we just about crammed it in the same box. So they were better than we were, unfortunately. But the reason I'm showing this one is because on the left, you see kind of a snapshot of the pattern. So that's 4 by 4 meters. The folds are about that far apart. So we did spend a couple of days folding. I'm very, very glad that job is over. But why am I showing this one? This is a Deorbit Sail. So the previous one was in orbit to use the sunlight to be pushed along. We designed this sail to use the drag in the orbit to slow satellites down. So you might want to use this, for example, as a deorbiting device for satellites. So a satellite is in orbit for about 15 years, 25 years. At the end, you want to make sure it burns up. So it kind of burns, so you slow it down until it hits the atmosphere and burns up. So you might deploy one of these things at the end of life to get a very large area, lots of drag, slow it down, and burn it up. So that was the motivation behind this work. And it takes me to my last 2 examples of origami in space. And again, this is one I worked on a few years ago. Similar idea. We have a big drag sail, not quite as big as the other ones, 10 square meters, but also had another origami component. And I'll show you a bit more detail in a second. But this was intended as a demonstrator. This also launched a few years ago. And the idea was that this would be attached to a satellite. You would deploy it at the end of life. As a test case, you have this deployable boom, which I'll show in a second, and then the sail comes out at the end. And so my work was to design the boom that connects the satellite to the sail. So I designed that, and it was an inflatable one. And I've got kind of a little demo here. So you had this boom on the far left. It folds up really compactly. Then you inflate it, and it will automatically deploy to a meter length. I can't fully deploy this, but you get the gist. This will become a meter long. Keep in mind, this all came from a satellite this big, right? So something this big, a meter long boom, and then this big sail comes out. So I spent a lot of time designing this. Really chuffed. We launched it about 2 years ago. But because it was a satellite this big, there was no camera on board. So we think it worked, because it came down very quickly, but we don't have proof. Now, that's where my final example comes in, because that same technique is on board this satellite, which is currently in orbit. This is called Remove Debris. It was launched from the ISS last year, and it's a mission which is designed to catch space junk and then bring it back down to Earth. So it has a couple of experiments on board, and they did a couple. If you go to the BBC website and search for Remove Debris, you'll see there's two experiments. One was a net, where they basically kind of had a small satellite which they caught with a net, and there was one where they harpooned a small target. So it's kind of like gladiators in space, nets and harpoons. But the final experiment is to deploy this system from that satellite. So hopefully, in a couple of months' time, I'll have a video of an origami boom in space with a sail at the end. So that's kind of where I want to leave it. So hopefully you've seen that origami is a bit more than just a paper crane. Engineers use it to solve really interesting problems. And as I was making this presentation, I realized it's kind of like a Marvel Comics story. We've got transformers, invisibility cloaks, and we're cleaning up space junk using origami. So that's it. Thank you very much.